Hey class, Mr. Muadin here with a continuation of what we would have covered in class were it not for the interruption. So here is a somewhat more complicated optimization problem, another classic of the genre, you might say. So just to review, as class ended, we were looking at the fencing problem where you have an optimizing function which is area, which has three variables. We need to have only two in order to make our lives easier in terms of what we know about calculus. So we combine that with a physical constraint, which is that we have limited fencing. And as one of our classmates showed us that we can describe the constraint as a function of perimeter and then simplify our function as we do in this step here by replacing y with 500 minus 2x. Critical numbers yield occasionally maxima. So we found the critical number as being 125. As the bell rang, I asked you to kind of test by plugging them into the derivative. Test values below 125 gives you positive, above 125 gives you negative, which indeed confirms this is a maximum. To find the y value, you would just plug 125 back in here, and I believe you get 250, and that makes for your maximum area, 250 by 125. Looking at another optimization problem, the second classic here, looking at a piece of cardboard that is a certain size, 14 by 10, and we're going to cut out corners and fold up the sides to form a box. So we got to find the height that'll give the maximum volume. So before I actually show you the visual here, I want you to try to visualize it yourself. So maybe pause the video for a moment, try to picture what this might look like. In order to understand how the size of the cut determines the volume of the box, right? If you had a piece of cardboard like this and you cut out pretty large pieces from the corners, what you would find is what remains, which is this thing right here. Right? These would fold to become a box without a top, just sort of a tray of sorts, right? And the bigger that these cuts are, right, the bigger these squares are, the taller of a box you would have. Okay? So with all that said, here's the visual. Hopefully it matches what you were visualizing in your head, or maybe even sketched out. And there's quite a bit going on here, so let me try to make sure that you understand where these numbers came from. This entire length is 14, right? When you're cutting out these squares of size h for height, as we saw that become the height, this remaining length here is 14 take away 2h. And by similar reasoning, what used to be 10, what remains is 10 minus 2h, right? So once you remove these four corners, what you're left with is this sort of large cross or plus sign type shape, and that folds into become this box right here. So there's quite a bit of visualization that's required to go from one to the other. Sometimes problems give you a picture, sometimes they don't. Here's one where you're given a picture, although I do encourage you to do your best to try to visualize it the best you can. That will help you make sense of the problem and persevere through it. So 14 take away 2h is one of the dimensions right here. 10 minus 2h is the other dimension, and the depth, so to speak, is the height of how deep the box goes. And again, the bigger the height, the deeper the volume. Although, of course, by the same token, the deeper the height is, the less wide it's going to be as well. So we have a physical constraint. So what we're asked to maximize in this case is the volume. So we need a volume function to optimize. So the next slide, I've done some of that for us already to save a bit of time. So volume of a box is length times width times height, nothing groundbreaking there. And I'm going to replace what we know about length, width, and height. So this being one of our dimensions, let's say length, this being our width, and this here being our height. So just plugging them in, we have that. This can be simplified. So you could double distribute or FOIL, whatever you want to call it, and that would achieve this right here. You then distribute the h, and you end up with this volume function right there. Now what's nice about this is it has only one variable, and that's height. So you have, two variables, the other one is volume, but contrast that with the area problem where you had area, x, and y. With 3, here you only have 2. So in a sense, this is not only the optimization function, it has its own constraint built in, which is to say that as h varies, so does the length and width of the function simultaneously, of the volume. So it also has its own constraint built in, and we can see that by having only one independent variable. So to maximize this, if you look back at the wording of the problem, it says find the maximum volume, right? So just we recognized from our previous experience that the maximum could occur to critical numbers. We need to find those critical numbers, or more specifically, with the derivative of the volume, in this case, equals 0. So finding the derivative is fairly straightforward, just a classic application of the power rule. So 140 minus 96h plus 12h squared. This is kind of a beast of a derivative, not to take, but actually to work with. So we want it equal to 0, which I neglected to put when I typed it ahead, so equals 0. This will give us critical numbers. Well, solving that can be a bit of a pain, so let's simplify it a bit. Through a bit of trial and error, I found that it's factorable by 4. And notice the 12 didn't go into 140, so I'm going to work my way down, and 4 seemed to work. So now it's really a question of factoring this. Now, I'll save you some time, just so you don't hurt yourselves trying to work through this. Unfortunately, it doesn't factor. Not into nice, rational numbers at least. Which means we have to use an old tool, one that we haven't pulled out of our toolbox in a long time, and that's the Quadratic Formula, which says that the independent variable, which in this case is h, but in general is x, is equal to minus b plus or minus the square root of b squared minus 4ac over 2a, where this is a, and this is b, and this is c. Okay, so notice that we're going to have two answers, as you might imagine, with a quadratic. So in class, this is an opportunity where I would ask you to quietly work your way through some of the algebra, and compare with your neighbors to see if you can work anything out together. But here I'll just work along with, and I'll pause the video, that way it'll be a little bit shorter. All right, and we're back. Here I went ahead and applied the quadratic formula to this particular problem. Worked my way through some of the algebra, arithmetic rather, and got 24 plus or minus the root of 156 over 6, which approximates to either 1.98 or 6.082. So these are my critical numbers. They are numbers where if I plug them into the derivative here, I will get 0. Now there's something curious about this problem. Oftentimes in calculus we get so caught up in the procedure we kind of lose sight of domain in terms of application. So the height could be 1.9 approximately, and it could also be a little bit more than 6. Well, one of these numbers has a critical, no pun intended, issue with it, a real major problem. So if I took away about 1.9 from these 14 by 10, well, it seems like that'd be reasonable enough, right? This whole thing is 10, and this whole thing is 14. And if I took away 2 from that both sides, it's not bad. What about taking away a little more than 6? Well, taking away a little more than 6 means I'm cutting in 12 from both directions, or 12 in total, giving me a very, very skinny length remaining here. But I cannot take away more than 6.08 from 10, right? The two squares that I cut out are going to obliterate the entire cardboard here. So in a sense, my domain of this function, which we didn't consider earlier, is going to be a maximum domain of 5. I cannot cut away more than 5, because if I did, I'd be just cutting the cardboard into 4 distinct pieces, right? So we kind of already know that this answer right here isn't really going to make much sense. Now, we can also eliminate it using some other methods, but nevertheless, if we don't identify it now, we'll still be okay. But it's important to realize that this physically does not match with our experience. So the question is this the maximum volume? Well, let's try some numbers out. If I plug in 1 into which is less than this, right, so I'm not doing the full number line, but just kind of working our way through it, I should get an increasing or positive increase in V or positive V prime when I plug 1 in. So 140 take away 96 plus 12, I believe will indeed be positive. It's I'm not taking away a whole lot, and I'm adding some more. So that's going to be positive. And I plug in something like, let's say, 3. So 140, I'm just doing some calculation here off screen. 140 minus 96 times 3 plus 12 times 3 squared, and you get a negative 40. So plugging in more than 1.98, I get a negative value. So before is positive derivative, after it's negative derivative, so that is indeed a maximum. So let's look back at what the question says. Is it find the height or is it find the dimensions of the maximum box? Determine the height of the box that would give it a maximum volume. Well, there we have it. The height is 1.918. So quite a bit to take a look there. The geometry of it is a bit of a challenge to visualize how you go from the words to this. Your optimization function is your volume function. The wording kind of gives that away. Your constraint is, in a sense, built in because you don't really have explicit lengths and widths. They're already sort of given to you there in the picture. Take the derivative, find critical numbers, and then determine whether it's a max or not. All right. Homework, if you missed it in class, is right here, page 220, number 17 through 21. Recall that in DS on Thursday, we do some makeup time for time missed from our quote-unquote snow day. So we will look at related rates in more detail that day. So keep that in mind. All right, see you later.